Hello, my name is Francisco Sanchez, and I'm going to be presenting our topic for this project 2. We're doing AC motors, also known as induction motors. This is pretty much the general setup of one. It's pretty much the shell. We're going to have to do a couple of simplifications just to make things easier for us. So our first simplification is we're going to assume a perfect transfer of energy. Why do I say that? Well, induction motors work like this. There's an electrical aspect. You put a little shaft in and it turns. That's what causes the mechanical energy. We don't want to explain any of that. So we're just going to say it's a perfect energy transfer. All the electrical stuff works and it works out in the mechanical. We're also not going to go into the full process behind how these things work and all that. We're just going to focus on what specifically pertains to this class. So let's get some terminology down. I originally called this just a shell. It is more than just a shell. It actually has a name. It is called the stator. It is where the coils and stuff will be wrapped around. Braden will touch more on that later, but basically, this is the stator. What's going on inside the stator? Well, inside the stator is a thing called a rotor. A rotor would fit in here. The rotor's what's spinning. It's spinning because of something that the stator does. Braden's going to go into that. So I'm going to pass it over to him so he can get more into it.
Okay, so induction motors are also called AC motors, which stands for alternating current. So we're going to just quickly define what that is. We've been working with DC current. DC stands for direct current. So say, for example, you have current going this way in this loop. The light bulb's going to light up. But, for example, if the current was going the other way, the light bulb would still light up, right? The light bulb doesn't really need a specific direction of current in order to light up. It's still going to light up no matter which direction the current is facing. This is essentially direct current. It's current that's going only in one direction constantly. The value doesn't necessarily have to be constant, but what's important is that the direction of the current isn't changing in the loop. Alternating current is kind of what it seems like. It's when the direction of the current is alternating. So I don't really know what causes this. It's not really related to anything we're going to talk about. So some device can make this happen. But in an induction motor, you have a wire that has current alternating through it. So for like X amount of time, it could be going this way, and then it switches. X amount of time, it goes this way, and it just keeps doing that for you could set it for the same time interval. It'll keep doing that over and over, and that's alternating current. So we have this wire right here. If you have current going up, then your fingers curl in the direction of the magnetic field. Pretty basic stuff. Coming out of the screen here, going into the screen like this. This is also a nice visual representation of what that looks like. If you take this wire and coil it, it does two things. Number one, it becomes an inductor, and the reason that you coil wires like this is because the strength of the magnetic field produced will increase. Lastly, this is just like a bar magnet. Anything metallic that acts as a magnet, the direction of the current will flow from the south end to the north end typically. These are all some kind of basic things that we're going to be using to describe induction motors from here on out. Okay, so another thing I should have mentioned is that the reason that the magnetic field another way you can think about how the magnetic field will increase when you coil wires is like bricks. If you just have like a single row column of bricks stacked up, I could punch that and it would just blow out instantly. But if you take these bricks and you line them up like behind each other and I punch that, then my hand is shattering instantly. So the strength of the brick wall increases, much like if you coil the wires, the strength of the magnetic field is going to increase. So with an induction motor, you have something. I'm going to just demonstrate it like this. It looks more complicated in actual diagrams, but this is a very simplified version. So if you take one coil and another coil, then the magnetic field that is produced, assuming that this is the south end and this is the north end, the magnetic field is going to go like this, right? Assume current's flowing this way. When you have alternating current, what that does to something like this, ignore the circle for now, but what that does to something like this is it constantly causes the polarity of the magnetic field to change. So what's going to happen is as the device that makes the current change direction acts, like let's say you want current to change every 5 seconds, then every 5 seconds, it's going to take that long for the polarity of this field to change, so that after 5 seconds, north will now be here, south will now be here, hypothetically speaking, like this isn't a magnet, but I'm just using the south and north to better illustrate like direction of magnetic field. But the magnetic field would then be going down like this, so the arrows would be flipped, and that would just keep changing every 5 seconds. And the importance of this, everything that I just said, I want you to take away that the magnetic field is changing when you have alternating current. And if you have an object, let's say a metal loop, because a metal loop can act like a bar magnet because it's conductive, if this object is inside of a changing magnetic field, then an induced electrical field is going to occur on that metal loop. So let's say it would be going this way. And obviously, as the current changes polarity, this electric field would flip in direction. But this electric field is induced on the inner metal loop, and this causes a voltage to be induced around the loop. This voltage is equal and opposite to the change in flux of the loop. Now, what is flux? Flux is a measure of the change in magnetic field. So we're almost there. We're going to use Lenz's law to finish this thing off. I have a quote here from the textbook Physics for Scientists and Engineers. It says, "There is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing." This is the definition of Lenz's law. So what this basically means is we know that the magnetic flux is changing because the magnetic field is constantly changing polarity. Therefore, current is induced in this inner loop because the flux is changing. That's straight up Lenz's law. So the fact that there's current now induced in this conducting metal loop means that it has its own magnetic field, because as we explained, with current comes a magnetic field that is generated. So when you have this magnetic field interacting with this magnetic field, you could think of it like bar magnets. What's going to happen? So I had this loop here from our stand earlier. If the loop is like this, then just assuming random polarities, it doesn't really matter because alternating current is going to make different polarities happen at different times. If you have this loop right here, obviously you can see it's going to want to spin this way to go into a stable equilibrium. But if you just happen to have the loop oriented in either of these two positions, where here you can see it's in an unstable equilibrium and here you can see it's in a stable equilibrium, then when you turn on the motor and current starts to change, this thing isn't going to rotate. In fact, this thing, when the loop is like this, it's only going to rotate like 90 degrees, and then it's going to go into a stable equilibrium. So there's a problem here. Yes, this causes rotation, but only in special cases, and it'll eventually stop at a stable equilibrium if it can. So what you need to do is introduce multiple of these into the system. So you would take this and put another one like right there, and then you would take another one and put it right there, so that when the magnet reaches a stable equilibrium from one, it's always already feeling a force from the other set of inductors, and it's going to continue to spin. Same like this. Another small thing is that you also need to offset the phase angle for when you start each current. Like all currents from each of these sets of inductors are going to be different. They're going to be started at different times, because if you don't start the alternating currents at different times, then the motor can jam as well, because it can end up in a stable or unstable equilibrium. Now, stable and unstable equilibriums, you can think of it like the roller coaster example that we used in 212. So if I have something like this, then a point up here is going to be an unstable equilibrium, because it's not moving, but it wants to go down here or down here, which are going to be stable equilibriums. Okay, the last thing we need to tie this all together. Before we were looking at the loop kind of like this as it's rotating, but this is like a frontal view, so now the loop would be spinning like this. It's the same thing. I've just oriented it from like a frontal view versus like a side view. So we have 3 different sets of inductors that all cause rotating magnetic fields. Now, I say rotating because from this perspective, the magnetic fields are going to rotate like this. And in this perspective, the magnetic fields are just going to be switching polarity, but it's the same thing, just looking at it from different angles. So you have a magnetic field from like the blue that'll go like this, and that will be it actually changing polarity. And this is the beauty of induction motors, is that you can have something like this and model it as rotating magnetic fields. This is the stator, this is the rotor. Now, why am I saying all this? Because we're going to do something awesome. We're going to talk about slip. Slip is the fact that the rotor has to turn at a different speed than the rotation of the magnetic fields. Why does this have to happen? Well, think about it this way. In order for this to happen, a current has to be induced in the wire. A current can only be induced in the wire if the magnetic field or flux is changing. But if your rotor is rotating at the same exact speed as the magnetic fields are rotating, then to the rotor, the magnetic fields aren't even rotating. It's like if I'm the rotor and I took this is the magnetic field, and I go like this, like to me, the magnetic field is not changing. To me, it's just constant because we're both moving at the same speed. But if I take this and I'm like turning like this, I'm trying to demonstrate it, then I'm turning slower than the speed of the magnetic fields are rotating. Then there's an obvious and apparent difference in magnetic field that I'm experiencing. So slip has to happen in order for an induction motor to work, where the rotor has to spin at a slower speed than the spin of the magnetic fields or the switching in polarity of the magnetic fields. And honestly, you don't even have to do anything to make this happen, because it already happens due to things like friction between the system, like heat, other factors that you don't really have to control. Whatever the rotor's like spinning could provide some resistance. So in most scenarios, you don't even have to do anything to minimize slip, because it just occurs naturally, and that's really cool.
All right, so the coils that Braden referenced that are in the AC motor circuits are actually solenoids, like this problem. And those solenoids create a magnetic field because they're wound up current. And these kinds of coils are what induce the current in the rotor, which creates the magnetic field from that. And so the change in magnetic flux is what's creating the induced current inside the actual loop of the rotor, which is like this problem in Homework 9, Problem 2. Because just like an AC motor, a current is being induced in the loop by the change in flux according to Lenz's law. The difference is that in an AC motor, the change in flux comes from the alternating current moving up and down, which changes the magnetic field, which changes the flux. But in this problem, it's just the change in radius that creates the change in flux. So an AC motor is actually more similar to this get ready problem from number 18, where it's the change in magnetic field that causes the change in flux. Because similar to an AC motor, since the alternating current is switching from positive to negative and going from negative to positive again, that changes the field, which is the change in flux as well. And so with that induced current, it creates a magnetic field from itself from the rotor. And because it has a magnetic field, it'll want to spin to reach magnetic equilibrium. Just like in this problem from Lecture 17, Exercise 1, where we were trying to find how the magnets would react to the current underneath it. The rotor will also spin like these magnets, but the difference is that in an AC motor, we don't want the magnets to actually reach equilibrium, because then they will stop. And so to keep the magnet spinning, that's why we have the magnetic field offset. Just like Braden talked about, there's a spin difference offset so that the magnets will keep spinning and never reach equilibrium.